we're going to look at section 10.4, and we're going to look at a summary of all of the conic sections. Okay, so if you look at the generalized formula, in the book they don't even include this term, so it's just missing. But I thought I would include it here because it kind of seems weird that the coefficients they're using go from A to C and they skip over B. And that's because we just don't use this term, but in the general form, we usually assign that to B, and they follow that same pattern. But you might just kind of wonder, like, what happened to B? So I put it in there to show you. So this term is always missing. So for us, B will always be 0. When we open up Desmos in a minute, you'll see that this B term, the BXY, has the effect of taking our major axis or our transverse axis, and instead of it being horizontal, strictly horizontal or vertical, it will rotate it. So if we have a value in there for B, the whole graph will sort of rotate. So we don't do any like that. That gets more complicated. So for us, B will always be 0. Okay. Also notice that we did not specifically cover circles in this chapter, but circles, as was evident when we sliced through our cone of light, circles are certainly possible when you slice through a cone. And they are technically a conic section. Our book just has circles in an earlier chapter, but now that we're reviewing all conic sections, we're including circles with them. Okay, so well, this table here, oh, also if you look on page 992, that's sort of a good list of all of the conic sections, when the major axis is vertical or versus horizontal, when the parabola opens up or down or left and right. So all the conic sections, so it's a nice concise list of all the different conic sections and all of the characteristics. So you might go look at that. All right, but what we want to concentrate on here is how can I look at an equation in this general form and determine which of these things it is. So I'm obviously a parabola. You know this one's a parabola, right? Because I'm telling you it's a parabola. But what about, in particular, the A and C values make this a parabola? All right, so let's list. Well, what is the A value? In this case, A value, there is no x squared term, so that means A equals 0, right? That would be a sideways parabola, but I think you can think, if you think for a second, you see if it was an up and down parabola, opening up, opening down, then you would have a y and no y squared, and you'd have an x and an x squared. So either A has got to be 0, or C is equal to 0, but not both. So if we think, what would happen if both A and C are 0? Remember, B is always 0 for us. So if this part of the equation's missing, what do we have, right? So yeah, a line can be technically considered a conic section. It's sort of a conic section that's been sort of I don't know what the right term would be, but it kind of degrades down to a line. So technically, yes, you could consider a line a conic section, but we don't tend to do that. Okay, so not both, because if they're both 0, we would just have the standard equation of a line. Okay, now this is called the general form. In a line, that would be called the standard form. And, depending on the book and where you look at the book, this sometimes might be referred to as standard form, like when we had a line. But general form is kind of what we'll use here. All right, so what happens when it's a circle? What are the relationship between A and C when it's a circle? Here's an example of a circle. All right, so you know that A must equal C, but of course, they cannot equal 0, right? I mean, obviously, for obvious points we just talked about, if they were both equal to each other and equal to 0, then we'd have a line. So for a circle, it can, A and C have to be equal. We'll have a little bit of a caveat with these two as well. It's not quite enough. We'll talk about down here with some examples. But for the most part, if A equals C and they're both not equal to 0, you're going to have a circle. All right, what about an ellipse? What do you notice about A and C in this case? A is not equal to 0, all right? And then we know that the product of A and C, when I multiply A and C together, they should be greater than 0, all right? So, you know, if one's positive and one's negative, well, that takes us down to a hyperbola, right? So the signs have to be the same. They could both be negative, and if they are both negative, then this sign would have to change as well, because then we take it to the other side. It would be negative, and then when I divide through by a negative, all the negatives go away. So they can't be equal to each other, and they really have to be, what this is saying, they really have to be the same sign, right? They both either have to be positive or both be negative. Assuming, of course, the constant is the correct sign to correspond with that. All right. And for a hyperbola, what do you notice? You know, A times C, like they're different, right? I mean, they're different. You might say, I suppose you could say that A is not equal to C as well. One's going to be positive and one's going to be negative. They could have the same magnitude, right? So the absolute value of A and the absolute value of C could be the same. They don't have to be. They could be the same. So this could be 2 and this could be minus 2. That's fine. The box we draw for the hyperbola would just end up being a square. So that's possible. So they're not equal, right? I mean, of course, they can't be equal because one's positive and one's negative. So that's kind of, you know, goes without saying. Of course, they have to be not equal. One's positive, one's negative. But the product, probably the best way to think about this is the product of the two must be less than 0. That means their signs are different. So that's really what has to happen, is that their signs have to be different. And of course, if their signs are different, of course, they're not equal. All right, so if you open, click on the Desmos at the sort of the top of your notes for 10.4 here, it should open, if you click on in the PDF, should open Desmos that I have saved, that I've created. Okay, and so you can see that I have set up a bunch of sliders here, and they all have the ability to change a bunch of values. So, so if I change my A, for example, you can see that it changes my ellipse, right? So you can notice A and C are different values, and so they are an ellipse. Now notice too that if I were to change some of my F values, the graph may just completely disappear depending on you know, some of my other values. So just because, yeah, so for example, there's no graph here in this case, right? So it depends on what your F value is as well, whether or not the thing actually exists, right? It can go down to a point. Again, Desmos doesn't do a good job of displaying graphs that sort of degrade down to a point, so they don't really display that. But you can see that, yes, C and A are different. C and A are different, so therefore we should get an ellipse. They're both the same sign, right? If I switch over and make C negative, now A and C have different signs. Now I've got a hyperbola, right? So assuming the graph exists, then A and B should be different signs. And so if I swap over, there's an ellipse again. You know, there I have A and C different signs, and again another hyperbola. Also notice that when A and B are the same, I've set these sliders up so they're nice integers. That way it's easy to kind of make them the same. When they're the same, we get a circle. All right. When they're the same but opposite, so let me make one 8 and one negative 8, then the box that you would draw through which you are going to graph your asymptotes would be a square. So in this case, that means that the slopes of those two lines would be the asymptotic lines would be 1 and -1. All right, so let's go back to an ellipse for right now. So here's an ellipse. Let's make it a little bit longer. All right, so there's an ellipse. Now notice what happens when I change B, right? So B sort of rotates the axis, right? So the major axis, instead of being the major axis being horizontal or vertical, B gives us the major axis on a slant. All right, so you can see we've seen these kinds of things in earlier chapters when we had skewed asymptote. So this is a perfect example of a vertical asymptote and a skewed asymptote, right? So that's why B can come into play there. So we will not have B be anything be 0. Notice too that C is 0, so I got a parabola. If I make C positive and A 0, again, I got another parabola. Okay, and then I think we already saw when they're the same, A and C are the same, we get a 0. But again, remember that just because A and C have the relationship we said, the graph may not really exist. So you can see, like in this case, there is no graph because of the value of F, and also maybe E and D have some effect on that as well. Okay, so if the graph exists and it's not a point, then the A and the C relationships are going to tell you what sort of conic section we have. So in the let's look at some examples here. They're asking us to expand this. Well, first of all, let's think about which of the conic sections this is. This is the exact conic section of a circle, right? That's the radius squared. And then the center would be at 5, -2. But they're just asking us to practice expanding this out. So this will be x squared minus 10x plus 25. And then this will be plus y squared plus 4y plus 4 equals 25. And then if we set it equal to 0, we get, and let's just kind of put it in the same form of the general form of the equation, x squared plus y squared minus 10x plus 4y, and then plus 4 equals 0. So again, we know this was a circle, and we're just kind of verifying, sure, the A and the C are equal to each other. They're each equal to 1. Okay, so let's go on to this one. This one looks like a circle as well, except there's an issue here. This is a circle with a radius. That means r is equal to 0. So what would a circle of radius 0 look like? Think about a circle centered at 5, -2 with 0 radius. So that would be just the point. And so this is a point. Of course, we could expand that out if we wanted. But the whole point is you can tell that this is a point because in this form, it's set equal to 0. So if we expanded that out, it'd be similar to the one over here. We'd end up with what? X squared plus y squared minus 10x plus 4y. And then what do we have? We had 29. So plus 29 equals 0. Okay, so if we are going to expand it out and set it equal to 0, that's fine. But ultimately, you can't tell for sure that it's a point. To tell whether it reduces down to a point, you have to sort of have it in the HK form, not the general form. So from looking at this, it looks like, oh yeah, this A and this C are both equal, so this should be a circle, right? Well, it's a circle with ends up being radius 0, so that just condenses down to a point. All right, let's move on. Look at this one. So this is what shape? I think you can tell that this is an ellipse. but let's expand it out. Let's put it into the general form. I'm going to multiply through by 8 to clear out my fractions. So that leaves me with a 2, x minus 2 quantity squared, plus y plus 1 quantity squared equals 8. Okay, so I multiplied through by 8. And now I just want to expand these out. So I'm going to expand this, and at the same time I'm going to distribute my 2. So this ends up being 2x squared would be minus 4x, so it's minus 8x. This will be a plus 4 times 2 is a plus 8. And then this one, y squared plus 2y plus 1 equals 8. And so now let's put it in general form, set it equal to 0, combine like terms. We get 2x squared plus y squared minus 8x plus 2y. The 8's are going to cancel, leaving us with plus 1 equals 0. Okay. Now, this one looks a lot like this, except notice that this is a 0 over here. So just like the 0 up here caused this to be a point, the same thing will happen to this one. That will cause it to be a point as well. Think about if we were to reduce it, it's like an ellipse, where the major and minor axis are sort of both 0. It would condense down, collapse down to a point. If we want, we could do a similar thing. This would be what? 2x squared minus 8x. We'd multiply through by 8, right? 8x plus 8 plus y squared plus 2y plus 1 equals a 0 this time. And so 2x squared plus y squared minus 8x plus 2y plus 9 equals 0. So by looking at this, you can just say, oh, okay, so that and that, A and C, they are not the same. They're both positive. So that means this is an ellipse. However, again, you have to be careful. You can't just tell from that. I mean, if you know it's an ellipse, you know that those are the same. Those A and C are different. But in this case, you cannot eliminate the possibility that it would collapse down to a point. So you just have to be careful. You need to look at this form as well as this form to be able to say for sure that it is the shape that we think it is, all right, that it's not just a point. All right, so moving on to this one, notice this has a negative over here, right? So that's going to cause us a problem. This can't have a negative. It would be like saying the r squared is negative, right? So can't have that. This ends up being, no graph at all. And if you go and you put some of these in Desmos, just be warned, Desmos does not do a very good job when an equation plots down to becomes a point. I'm not sure it will actually display the point for you. Desmos has some limitations. It'll give you this graph fine, but I don't think it'll plot this graph as a point. So if you change that 25 to a 0 over here, Desmos will just give you a blank screen, I think. So if you decide to try to plot some of these in Desmos to check your answers, points tend to not show up. So, and also, of course, no graph, it would also not show up. Okay. All right, so let's go on to this one. This one has a negative in it, so this one is clearly a hyperbola. Let's multiply. In this case, the a squared and the b squared happen to be the same, and they can be. That just means that the box is going to be a square. The box through which we draw our asymptotes, right, to guide us to draw the hyperbola will be a square. Okay, so let's multiply through by 4. That gives us y minus 1 quantity squared minus x plus 1 quantity squared equals 4. And then let's expand these out. We get y squared minus 2y plus 1. And then careful, we are going to expand this out, but also I'll distribute the negative in there. So we get negative x squared would be plus 2x, so it's going to be minus 2x, and then minus 1. Let's go ahead and just bring the 4 over. Minus 4 equals 0, because we want to set that equal to 0. All right, and then finally, technically we want the x first, so it'll be negative x squared plus y squared minus 2x minus 2y. And then these ones cancel, so negative 4, subtract 4, equals 0. So again, here you can see that that the A and the C, the magnitudes are the same, but the product of A and C is negative, which is what we'd expect here, right? They're clearly going to be different, but they have to be opposite signs. Okay. So now when you first look at this one, you might say, oh, this was no graph up here, so this one should be no graph. Well, that's not exactly true, because I can multiply through by a negative to turn that into a 1. If I multiply this through by a negative, that would make these two things negative, and that can't have that, right? For an ellipse, you can't have that, or for a hyperbola for that matter. So here, when I multiply through by a negative, the signs are going to change. So it looks like the transverse axis is vertical because the y is positive, but as it turns out, the transverse axis will be horizontal because the x will end up being positive when we do that, okay? So, that would end up looking like x plus 1 quantity squared over 4 minus y minus 1 quantity squared over 4 equals positive 1. And you can expand that one out. It'll be similar to this one over here. Let's move on to number 8. And then, so what shape, what conic section is this going to be? And you can see this is clearly a sideways parabola, because it's x, right? There is no, a in this case equals 0. There's no x squared term, so clearly it's a parabola that opens up sideways. All right, so let's set that equal to 0. Let's put it into the general form as well. All right, so I'm going to expand this and distribute that in, so we get x equals negative, not negative, sorry, x equals 1/2. That's y squared. That would be 4. Half of that is 2y plus 4 or plus 2, and then minus 5. Okay, so I expanded that and distributed the 1/2 in there. Now let's bring everything to the other side. The x squared is missing, so we're going to leave that off. Actually, let's take it'll probably be faster to take the x that way. So we're going to have 1/2 y squared minus x plus 2y, and then minus 3 equals 0. If you want it, you could think of it as a 0x squared if you wanted, but we would just leave this one off. But you can kind of see that clearly a is 0, just putting them in the same order as our general formula up above. Okay. All right, so that this whole section is about sort of identifying what the graphs are and practicing some of that. Let's move on to this last thing, sort of an extension of the eccentricity that we were talking about. Remember, eccentricity is c over a, but we're going to expand that into talking about ellipses, parabolas, and hyperbolas. Now, of course, c over a doesn't make sense for parabolas because there is no c or a in parabolas. Now, there's an a, the leading coefficient we call a in a parabola. But remember, for the other conic sections, a is the distance from the center out to a vertex, or a center out to the endpoint of the major axis. The book sometimes refers to that as a vertex. In my past books, I haven't been comfortable. They haven't used that term, so I'm not really comfortable calling that a vertex and that a vertex, but you certainly can call it that. Okay, so so we have an A and a C, and C, remember, is the distance from the center out to a focus, well, we don't have a center here, right? We have a vertex and we have a focus, but we don't have a center. Like, we don't know, well, what's the distance from the center to the vertex for a parabola? Well, we don't know because there is no center for a parabola. So this definition doesn't really hold perfectly. So one definition is that, we define each of these things. The ellipse, right, is the definition of the distance from this point to this focus plus this distance to that focus, right? That is the definition, the set of points, right, of that's an ellipse. The sum of those distances is constant. So we have another way of looking at it. The distance from a point to the directrix and a point on our conic section to the focus is a ratio, a set ratio. So the distance from the point to the focus divided by the distance from the point to the directrix is a constant for every type of conic section, and that is the E. Now, for a parabola, E is always 1. So this distance from focus to point and from point to directrix, those distances are the same. So the eccentricity of a parabola is always 1. So we know that that ratio is always 1. Now, the ratios for hyperbolas and ellipses, now we can say, okay, for those two situations, we can also kind of think about this as being C over A. Now, that does not mean that the distance from a point to the focus is C. This ratio will be the same as this ratio. Individual values will not be the same. Again, this only makes sense for these two. All right. And so for an ellipse, the distance from a point to the focus divided by the distance from the point to the directrix will always be less than 1. So this length will always be longer than this length, regardless of where that point is on the ellipse. All right, we also have another focus and another directrix on the other side, however. These are symmetrical, but if you're dealing with this focus, you're dealing with this directrix, all right? And then for a hyperbola, we think about a point, so the point from a distance from the point to the focus, and then from the point to the directrix, that ratio will always be greater than 1. So this length will always be the greater of the two. And again, that's dealing with this focus is corresponding to that directrix. So the focus over here would have its own directrix over here as well. Okay, so those distances, the distance from a point to the focus is always greater than the distance from a point to the corresponding directrix. So this point focus deals with the one directrix, the other point deals with the other directrix in this case. All right, so click on the Desmos in the sort of towards the bottom of your PDF this time, and it'll open up another file that I created on Desmos for you. This one is going to use sort of the definition of the conic section using eccentricity to define basically the conic section. So what I've done here is I didn't do the general form, I just did an ellipse. You can see that's in red here. So I centered it at 0 just to keep it simple. The only thing you can really change is the A and the B. For the sake of this experiment, don't make the major axis vertical by making B bigger than A. Everything is kind of based on certain values of the focus, and the focus is no longer on the horizontal axis. So just for the sake of this demonstration, make sure that you keep your A and B values such that A is the bigger value. If I make B bigger, then it just changes the major axis vertical. We know still that's technically A up there, but Desmos has some limitations. So just make sure that your ellipse is has a major axis that's horizontal. Okay. I've also made a point here. It's controlled by the slider up here. I called it D for no real good reason, but it's just called D. You can also grab on the point itself, and that changes the slider. So, all right. So for an ellipse, for any given ellipse, the distance from the point to the focus divided by the distance from that point to the line called the directrix is going to be constant. And not only is it going to be constant, it's the eccentricity of our conic section. Of course, that ratio will change as I change my ellipse, right? So if I make my ellipse, I don't know, let's say you make it more circular, then now I can see clearly the ratio of the blue dashed line to the purple dashed line has gotten smaller, right? The blue line is much smaller than the purple than it was before. As I change my shape, now the purple and blue line are similar in shape, similar in length, a little bit more similar. They weren't really different. And so, but what it says is that or in this case the ellipse. Also, Desmos tends to deal with things as functions, so my point is limited to the half of my ellipse. I have 2 points, and then certain other things it would know which point to use. So it tends to look at things as functions sometimes, and so it's only points only available to us on the top half of this ellipse. But it's good for demonstration purposes. Okay. Also, you can't create on a hyperbola here. This demonstration tool is strictly for an ellipse. What I was interested in exploring was what happens when it becomes more and more circular. So as I become more and more circular, notice that the directrix goes further and further out. All right, let me move my point up a little higher here. And so if I make the ellipse more and more circular, and then, so as I do that, notice the directrix goes further and further out. Let's make it pretty close to a circle, and then let's go find that directrix. How far out is it? Okay, so it's pretty far out, but notice that it's not a circle because A and B are not the same. But if I make A and B the same, boom, now it's a circle. And now if I zoom out looking for that directrix, that's not there. And so it's infinitely far away. You can go over, spend all day going over, and you'll never find it. And that sort of reconfirms the whole idea that the eccentricity of the circle is 0. The distance from the point to the focus is not 0, but the ratio from that point to the focus and divided by the distance from the point to the directrix, because that distance, the point to the directrix distance, is infinitely large. So the ratio of those is technically 0, because anything divided by infinity will be 0. And so we'll see that you'll see that idea more and more next year when we talk about infinities more and limits. Okay, so I just wanted to sort of look at this. If you feel like it, again, make sure your B is smaller than your A, otherwise it just doesn't work. The I'm on here for the lines kind of disappear. All right. And then your homework is listed here.